Hello and welcome to the 20th topic in this course. We're moving on to looking at programming languages, the theory behind them mainly. First of all, it's worth looking at what I'm going to call the programming language spectrum. And first of all, we need to talk about what machine code is. And machine code is essentially the lowest level of programming language. It's the simplest form possible, and it's expressed completely in binary. We know by now that computer code needs to be in binary. A computer only can understand binary. It can only understand digital data, and binary is just ones and zeros, and it can understand that it can't understand words unless it's been translated into binary. So machine code is basically just a stream of binary digits and instructions in the form of bit patterns. And this video sort of links quite nicely into another one I did about representing instructions in binary a while back. Because a lot of the stuff is directly linked, although it's not in the same order. And I'm using this this image or this sort of spectrum graphic I did in that video. In this video, just quickly to show you. So I should just finish what I was about to say. So machine code can be executed directly by the CPU, the processor. Although it's really worth noting that machine code is specific to each model / make of the CPU, because each CPU has its own instruction set, a way of representing instructions, and a machine code. So if you had this stream of ones and zeros and you gave it got executed by another CPU with the one it came from, it would do something slightly different and may not even work, because they each use different ways to represent instructions. And so machine code is unique to each CPU, which is one of the reasons why programming languages are used instead. But if we talk about the spectrum, at one end we have these ordinary languages. We have English as our language, and then we have machine code at the other end. This is just an example. Maybe you wouldn't take it too literally. I mean, English isn't really a type of programming language, although I guess you could argue it is, but anyway. So you have these low-level programming languages and you have high-level programming languages. They're not to do with ability, that's what connotation of high and low is, but they're more to do with high-level programming languages and mainly English. Or they're not completely binary. So machine code is completely binary, you mentioned. We then have assembly languages, which fall under the category of low-level programming languages, and they're not completely binary, but they're slightly more user-friendly. It would be very difficult just to write in ones and zeros over time. It used to be done when computers were first invented. People just used to write in ones and zeros, but it's not really useful. So instead they use simple mnemonics like add. So they use simple. So they use maybe hexadecimal and mnemonics just to make it slightly easier. So it's really basic. It's very, you have to learn how to use it. So you wouldn't use it just to program a normal piece of code. You would use it if you're programming the hardware directly, because it's slightly more efficient, because you don't need to translate it as much. We'll look at that in a second. So you don't necessarily need to know about low-level programming languages. You definitely need to know about high-level programming languages, and they're even more like ordinary language. So they use a lot of normal words, a lot of phrases that we use in our normal everyday lives. So they have something called syntax. And syntax is just sort of the general rules that a programming language has. They're sort of just like the grammar. In English, syntax is like the grammar. So they have quite strict syntax. You can't just write English and run it by a program. It just doesn't work. You have to follow the rules of a high-level programming language. But they are a lot easier to use. They're a lot easier to understand as well. You could just read. So Python's quite a good example. Python, you could just read and you could sort of understand, even if you don't actually know Python that well. And they're portable. So I've seen this come up in exam questions before, being described as portable. And this means that different computers can use these programming languages. A computer with a Intel processor can run Python, and so can a computer with an AMD processor. They're portable. They're not specific to each computer like machine code is. Although, as we'll look at, they get translated into machine code. But also another term that's not in a specification, but I've seen it in mark schemes especially. Source code is the written original form of code. It's what you write on your screen. That's what the source code is. And then the source code is converted into stuff called object code and then into the machine code. So source code is just the written form of code on your screen when you start coding. So you have something called translators, and translator is a utility program. We looked at this in our software video, but a translator converts code from one programming language into another. So it's important to realize that a translator will only translate the syntax of the rules not the logic or function of the code. So different programming languages, Java, C++, Python, will have different syntaxes. They write things in different ways, but their logic is very similar. And if you translated code from Python to Java, it should still do the same thing at the end, although the actual way it's done would be slightly different. So there are different types of translators, and they have different roles. So there's an example of a source-to-source compiler, which translates between two high-level programming languages. But if you want code to be executed directly by the CPU, it needs to be translated from a low level, from a high level programming language into machine code. And you're asked to know 3 types of translator. There's several more, mainly opposites. So there's a deassembler, decompiler, which do sort of the opposite. First of all, an assembler, and what this does, it converts between an assembly language. We looked at this just before, I didn't really talk about it, but basically a low level programming language into machine code. And so what it does, so I mentioned there being mnemonics used, and they're translated directly into the instructions in the form of bit patterns. Again, like I mentioned, this relates quite well to our instruction video, but there's a direct translation occurring here. The translator of a program takes these mnemonics and translates them into the machine code. A compiler we need to know slightly more about, or there's slightly more to talk about with a compiler. So a compiler, slightly different to an assembler, translates high-level programming languages into machine code. And what it does, the way it does this, it sort of does it all in one go. It scans the whole code first, and it translates it into the machine language in one go. And after it's translated, it can be executed by a processor. Compiled programs are stored as .exe files usually, and then when it's executed, an error report may be generated at the end. So that's different to an interpreter. An interpreter also converts from high level to machine code. But the difference is it translates the high level code line by line. It does it each line and then executes each line after it's translated. And what it does, it stops if an error is encountered, meaning that it doesn't do the whole thing. So if you had an error in the first line, it would stop straight away, whereas a compiler would go through the whole program just to tell you had an error at the start. So technically an interpreter is slower. If you had a program with no errors, if you used an interpreter as opposed to a compiler, it would be slower. But then if your error is really early on, it's not really ideal to use a compiler as opposed to an interpreter. So we move on to look at something called an IDE. And what an IDE stands for, and I would definitely recommend you learn this because this is an easy 1-mark question, Integrated Development Environment. And what this is, it's a piece of software that provides a collection of tools for a programmer. So there'll be IDEs for Python, the actual Python idle. They use idle for some reason. They use the airlit in develop to make idle instead of IDE. I don't know why, just to be different. But yeah, so an IDE is just a set of tools, and it could be given by the actual creators of a programming language. It could be sort of a third-party application. And we have several tools that make it easier for a programmer. They're the collection of tools. First of which we need to know about is an editor, and more specifically a text editor. And what this does, it allows the user to basically write the code. It allows it to enter code, to modify it, and so one of the tools it may have in this text editor, it may colour certain words. So functions like input here have been coloured in Python, prints a function, strings have been made green, for while the loop has been made orange. That just sort of, it does help. I mean, it helps if you're learning it, especially. It makes the code look slightly nicer to look at, I suppose, and maybe if you made a mistake, it shows it a lot easier. And some even autocomplete code while you type. I find that a bit annoying when that happens. It doesn't happen in the standard Python IDE that you may use, but it happens in some other IDEs where just actually you start typing print and it will do it for you, which I find slightly annoying, but some people may like. And I should mention the tools mentioned here. You could, in theory, write code in Notepad, save it as a file, use a translator that's off the shelf that you've either bought or downloaded. You can do all this separately. An IDE just combines it to make it a lot easier, and most people use IDEs when you program. So finally, or not finally, I should say, we've got error diagnostics here, and this could be a group of tools. So they have debuggers. You may have heard debuggers before. I think we talked about this before in a while ago. But they help just check for errors in your code. And often a debugger will just highlight when you have an error. When you're running it, it will highlight it, show you the line it's on, and may even tell you what's wrong with it. So here we get told it's syntax. Instead of doing else if, we've done, elif, we've done else if, which doesn't work because it goes against the rules of the programming languages. So then you have a another tool, the runtime environment feature of an IDE, and this is where the IDE runs the code as if it was being executed by the CPU. It sort of like artificially runs it. Obviously the CPU still does it, it just sort of translates it into an intermediate language that can be run by the IDE, so it sort of runs it through the IDE as opposed to just by the CPU. And it doesn't fully translate the code, meaning that if you have any errors you can fix them before the whole translation occurs, which will save you some time. And finally, we have auto documentation, and I find it slightly difficult to talk about because I've never used it myself. But what it does, it makes notes. It sort of comments on your code as you do it, and it may list your variables used. It may list what modules you've imported, and this is useful if you have large projects with lots of programmers working together because it shows you the list of things used, so you don't use them again, and it is just useful in that sense. So that's all for today's video. Hopefully it was useful. Next time I'm looking at control flow in algorithms, so hopefully you'll join me for that video.